Dear students, today we would like to discuss about the concept random variable. We can define the random variable. Random variable is nothing but assigning a number to a variable. Why we need to go for random variable? Why we need to assign a number to a variable? In the sample space, we'll be having, if you are having plenty of variables, it's not possible to remember all those variables, but we can. But being as a human being, we can remember the numbers. So we are going to assign a number to each and every variable present in the sample space. So for tossing the two coins, the sample space is ht, If the condition is number of bits equal, if the number of bits equal to 1, the condition is count the number of heads. Yeah, two heads are there, we can assign it to 2. Here one head is there, we can assign it to 1. Here also one head is there, assign it to 1. If there are no heads, so we can assign it to 0. One more definition of random variable is connecting the outcomes of an experiment with the real values. The numbers can be varied from minus infinity to plus infinity. Then outcome and real values together called as random variable or one-dimensional random variable. The two-dimensional random variable definition. Connecting two outcomes at a time to a one real value, provided those two outcomes should drawn from the same sample space. We define a random variable as a function of the elements of the sample space. Yes, the random variable is denoted by capital letter such as W, X or Y, capital W, capital X or capital Y, and any particular value of the random variable by a lowercase letter such as small w, small x or small y. Thus, given an experiment defined by sample space S, capital S, with elements small s, we assign to every small s a real number according to some rule called as random variable x of capital S. Random variable x can be considered to be a function that maps all elements of the sample space into points on the real line. For example, For example, consider an experiment consisting of rolling a die and tossing a coin. The sample space is shown in figure. Let the random variable be a function x chosen such that a coin head h outcome corresponds to positive values of x that are equal to numbers that shows up on the die. And the second condition is the coin tail T outcome corresponds to negative values of x that are equal in magnitude to twice the number that shows up on the die. Here, x maps the sample space of 12 elements into 12 values of x from minus 12 to 6 as shown in figure. You can observe here. This is the sample space for tossing a coin and rolling a die. Now, h comma 1. First condition is a coin head outcome corresponds to positive values of x that are equal to number that shows up on the die. That means here h comma 1 is there, so we'll be assigning it to 1. 2, 3 means 3, 4 means 4, 5 means 5, 6 means for 6. Whereas for t, second condition, a coin tail T outcome corresponds to negative values of x that are equal in magnitude to twice the number that shows up on the die. That means negative values of x means here T is there minus, actually we need to map it to minus 1, but twice that number means minus 2. Here t comma 2 means minus 4, t comma 3 is minus 6, t comma 4 is minus 8, t comma 5 is minus 10, t comma 6 is minus 12. It depends on why we need to assign to only for these values. It depends on the condition. Condition will be provided in the exam in the question paper itself. Second problem. Consider an experiment where a pointer on a wheel of chance is numbered from 0 to 12. The sample space consists of numbers in the set yes as less than yes is is less than or equal to 12. Let us define the random variable by the function s square. So the the random variable function is defined as s square. So 3 square is 9, 6 square is 36, 9 square is 81, 12 144. Here up to here we will do mapping. The conditions for a function to be a random variable. So very important. It is not necessary that the sample space points map uniquely. That is more than one outcome may map to a single real value. For the random weight set means x of lambda 1 equal to x of lambda 2 equal to minus 2, it can be that. But the random variable must not be multi-valued function. Multi-valued function means y equal to root 25. Root 25 is plus or minus 5. So root 25 is not a valued function. Since it is having multi-value the function which should be a single value. That is, every point in the sample space must corresponds to only one real value. The second condition, the set x is less than or equal to x is less than or equal to x shall be an event for any real number x. The probabilities of this event denoted by p of x is less than or equal to x is equal to the sum of the probabilities of all the elementary events corresponding to x is less than or equal to x. Third condition, p of x equal to minus infinity that equal to 0. P of x equal to infinity equal to 0. These three conditions are very important. Discrete and continuous random variable. Discrete random variable is a random variable in a finite interval. If a random variable assumes only a finite number of different values, then the random variable is called discrete random variable. The sample space for discrete random variable can be discrete, continuous, or a mixture of discrete and continuous points. For example, the number of telephone calls arriving at an office in a finite interval of time. The random variable assumes any values within an interval. It is called continuous random variable. This cannot be produced from a discrete sample space or mixed sample space. Is important. The exact time of arrival of telephone call is an example for continuous random variable. Mixed random variable is one for which some of its values are discrete and some of its are continuous. Now, the next topic is a distribution function and density function. Distribution function is nothing but distributing the probabilities to their corresponding random variable is known as probability distribution. The probability p of x is less than or equal to x is the probability of the event x is less than or equal to x. It is a number that depends on x and it is a function of x. Such function is called distribution function and it is denoted by fx of x. And it is called as cumulative probability distribution function of the random variable x. Fx of x is equal to p of x is less than or equal to x, where small x can be taken values from minus infinity to plus infinity. Distributing the probability values is nothing but probability distribution. Some of the properties of distribution function. Fx of minus infinity equal to 0. Fx of infinity equal to 1. From these two properties, from the definition of distribution function, we can verify these three properties. So always fx of x lies between 0 to 1. So property 4, property 5, property 6. Then they are important. Fx will be giving the proof of it. Fx of x1 is less than or equal to fx of x2. P of x1 is less than x is less than or equal to x2. That equal to fx of x2 minus fx of x1. Fx of x plus equal to fx of x. property 4, proof of property 4. The property 4 indicates the cumulative distribution function is a monotonic and non-decreasing function of x. So let us consider three events: x is less than or equal to x1, x lies between x1 to x2, x is greater than x2. Three events happen to be mutually exclusive, and some of their probability is given by this: p of x is less than or equal to x1, fx of x1, p of x is greater than x2, that equal plus p of x is less than or equal to x2, that is equivalent to 1. Since x is greater than x2 and x is less than or equal to x2, covers the entire range. So we are leaving this proof to students. Please go through the entire proof. If you have any doubt, please you can ask. And one more correction: properties 1, 2, 4, and 6 are used as tests to determine whether the given function is a valid distribution function or not. Two coins are tossed simultaneously. Let random variable x represent the number of heads. Sketch the probability distribution function. The sample space for the two coins of toss simultaneously is t, 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 h, h, t, h. Here x represents the number of heads. So here number of heads is 0. Here it is 1. Here it is 1. Here it is 2. So if x is 0 for tt, the probability for this is how many zeros are there? 1. So 1 by 4. For this, if x is one head, how many are there? One heads? 2 are there. These are the 2. So 2 by 4, that is 1 by 2. Here, 2 heads. How many 2 heads are there? Only 1. So 1 by 4. So if you draw these probabilities, like if capital X is 0, what the value for capital X is 0? 1 by 4. So we'll be drawing this 1 by 4. 1 by 4. X is 1. What is the probability? 1 by 2. From here, what is 1 by 2? X is 2. There is number of heads of 2. What is the probability? 1 by 4. So total probability is 1. Always the cumulative distribution function, the total probability maximum value is 1. It should be 1. So this is the cumulative distribution function. If x is a discrete random variable, fx of x must have a state step form such as an above. The amplitude of step will equal to probability of occurrence of the value of x where the step occurs. If the value of x are denoted by small xi, then fx of x equal to summation I equal to 1 to n, p of x equal to xi, u of x minus xi. In shorthand, we can represent this as p of xi equal to p of x equal to xi. P of x equal to xi can also be represented in short form as p of xi. So fx of x equal to summation I equal to 1 to n, p of xi, u of x minus xi. The probability density function is denoted by now. Up to now, we have seen the probability distribution function, that is capital Fx of x. Now we are going to define one more term, probability density function, which we always represent small fx of x, and is defined as derivative of distribution function. We often call as simply density function of random variable x, or probability density function. Small fx of x equal to d by dx of capital Fx of x. Now some properties of density function. 0 is less than or equal to fx of x for all values of x. This indicates that fx of x is a non-negative value or greater than 0. Second property is the area under the density function is always 1. The third property is capital Fx of x equal to integral of minus infinity to x fx of zeta into d zeta, where zeta is any variable. Fourth property: p of x1 is less than x is less than or equal to x2. Integral of x1 to x2 fx of x into dx. It relates to probability that x will have values from x1 to x, including x2, to the density function. The property 3 is just is another way of representing fx of x equal to d by dx of capital Fx of x, which is the link between capital Fx of x and small fx of x as follows. Small fx of x equal to summation I equal to 1 to n d of xi del of x minus xi. Properties 1 and 2 are used to test the given function is valid function or not. Check out the given function is valid function or not. This is a given function they have given. The first property, always fx of x should be greater than or equal to 0. So this is fx of x. The fx of x is always is here it is greater than 0. So the first property has been satisfied. The given function, the first, yeah. The second property, area under the density function should be 1. Here, it looks as a triangle. Area of the triangle is half into base of the height. So half into base of the height. Half into base value is this x naught plus alpha to x naught minus alpha. X naught plus alpha minus x naught plus alpha. The height value, height is a. So we'll be getting it as alpha a. Area equal to alpha a. Area equal to 1, that equal to alpha a equal to 1 by alpha. This is the second property. This is the density function. The next topic is Gaussian random variable. It's a very important. A Gaussian random variable x is called Gaussian if its density function is of this form. Fx of x equal to 1 by 2 pi 1 by under root of 2 pi sigma x square equal into e power minus x minus ax whole square divided by 2 sigma x square. Where sigma x square is greater than 0, ax values lies between minus infinity to plus infinity or real constants. Its maximum value occurs at x equal to ax. Here, its maximum value occurs at x equal to ax. Now its spread about the point x equal to ax is related to sigma x. The function decreases to 0.607 times its maximum value at x equal to ax plus sigma x and x equal to ax minus sigma x. This is the value. That is the e power minus 1 by 2. 0.607. The distribution function is found by fx of x for third property. Okay, question 1. Question 1. If you integrate this, we'll be getting it as this fx of x in capital Fx of x equal to 1 by under root of 2 pi sigma x square integral of minus infinity to x e power minus of zeta minus ax whole square divided by 2 sigma x square into d zeta. The equation 2 can be solved by numerical and approximation methods. To solve this, we need to develop a set of tables of capital Fx of x for all values of x with ax and sigma x as variables. However, this approach has limited values because there is an infinite number of possible combinations of ax and sigma x, which requires an infinite number of tables. So, further, a better approach is possible where only one table of fx of x can be developed that corresponds to normalized values of ax and sigma x. We often show that one table can be used in the general case where ax and sigma x can be arbitrary. We start with by selecting the normalized case where ax equal to 0 and sigma x equal to 1, denoting the corresponding distribution function by fx of x equal to 1 by under root of 2 pi integral of minus infinity to x e power minus zeta square divided by 2 into d zeta, which is the function of x only. For positive values of x, the tables will be provided. For negative values of x, we need to use this relation. So fx of x equal to f of x minus ax sigma x that equal to f of 5.5 minus 3 divided by 2, that equal to f of 1.25. Let's go through this problem. The next random variable is binomial random variable. The binomial distribution function can be used for the applications finite number of observations. That is tossing a coin, hitting or Bernoulli trial experiments, hitting or missing the target, passing a TED exam, receiving bit 0 or bit 1 in a computer stream, winning or losing a game, etc. Let us see that p lies between 0 to 1, n equal to 1, 2, 3, and so on. Then the function, density function, summation is given by summation k equal to 0 to n ck p power k 1 minus p whole power n minus k del of x minus k is called binomial density function. The binomial density can be applied to the Bernoulli trial experiment. Experiments having only two possible outcomes on any given trial. By integration, the binomial distribution function can be found to be summation k equal to 0 to n ck p power k 1 minus p whole power n minus k u of x minus k. These figures will be getting it as by substituting n equal to 6 and p equal to 0.25. The next random variable is Poisson random variable. The Poisson random variable x has a density and distribution function. Fx of x equal to e power minus b summation k equal to 0 to infinity b power k factorial del of x minus k. Fx of x equal to e power b summation k equal to 0 to infinity b power k factorial u of x minus k. The waveforms will be similar to the binomial random variable. The Poisson random variable can be applicable for wide variety of counting type applications. Example, which describe the number of defective units in a samples taken from production line, the number of telephone calls made during a period of time, the number of electrons emitted from a small section of cathode in a given time interval, etc. If the time interval of interest has a duration capital T, and the events being counted are known to occur at an average rate lambda and having a Poisson distribution, then B is given by B equal to lambda T. The next random variable is uniform random variable. The uniform probability distribution function and density function are defined by like this. Fx of x equal to 1 by b minus a, x lies between a to b, 0 elsewhere. Capital Fx of x equal to 0, x is less than a, x minus a by b minus a, when x lies between a to b, 1 b is less than or equal to x. The applications of uniform density function finds a practical uses. A practical important application is in the quantization of signal samples prior to encoding in digital communication system. Quantization amounts a rounding of the actual sample to the nearest large number of discrete quantum levels. The errors introduced in the round off process are uniformly distributed. Exponential random variable. The exponential random variable finds the application of exponential random variable will be using to describe the raindrop size or number of rainstorms when the number of rainstorm measurements are made. Small fx of x equal to 1 by b e power minus of x minus a by b, where x is greater than a, 0 x is less than a. Capital Fx of x equal to 1 minus e power minus of x minus a by b when x is greater than a, and 0 when x is less than a. The next one is relay density function, relay random variable. The relay random variable describes the envelope of one type of noise when passing through a bandpass filter. This is also important in analyzing the errors in various measurement systems. The distribution function and density function for the relay random variable is given as like this. The next topic is conditional distribution and density function. The concept of conditional probability. We know that P of A by B equal to P of A intersection B by P of B. Conditional distribution function is given by fx of x by b equal to p of x is less than or equal to x by b. That can be given as p of x is less than or equal to x intersection b divided by p of b. Properties of conditional distribution function is same as properties of distribution function. Conditional density function. Fx of x by b equal to d by dx of fx of x by b. The properties of conditional density function are similar to the properties of density function. Methods of defining the conditional event. We're having two methods. There are several methods actually. In our syllabus, we will be discussing in detail about two methods. The first method, even B, is defined in terms of a random variable x. The second method, even B, may depend on some random variable other than the x. That we'll be seeing in the second later. Defining the event in terms of x is capital B equal to x is less than or equal to b, small b, where small b is a real number, which where lies small b lies between, small b can take any values between minus infinity to plus infinity. Conditional distribution function, capital fx of x, capital F x of x by b equal to p of x is less than or equal to x by b, p of x is less than or equal to x intersection b divided by p of b. We substitute this one in equation 2, we'll be getting it as this. For all events x is less than or equal to b, for which this p of x is less than or equal to b is not equal to 0. Here we need to construct two cases, b is less than or equal to x is less than b, or b is greater than x. These two cases. The first case, if b is less than or equal to x, the event is a subset of the event. So we can write as p of x is less than or equal to x intersection x is less than or equal to b means that will be equal to x is less than or equal to b. Equation 3 becomes as like this. Fx of x by x is less than or equal to b becomes 1. Case 2. When b is greater than x or x is less than b. When x is greater than b, the event is a subset of the event. From equation 3, we can write it as like this. Here, fx of x is less than or equal to fx of x by x is less than or equal to b equal to fx of x divided by fx of b when x is less than b. So from equation 4 and 5, we can write it as like this. Fx of x by x is less than or equal to b equal to fx of x divided by fx of b when x is less than b. 1 when b is less than or equal to x. Similarly, conditional density function can be written as small fx of x by x is less than or equal to b can be written as like this. Small fx of x divided by capital Fx of b, that equivalent to small fx of x divided by integral of minus infinite to b fx of x into dx. The conditions are very important here. X is less than, for x is less than or equal to b. If x is greater than or equal to b, the value is 0. Here we have made an assumption that the conditional event has non-zero probability. So always fx of b lies between 0 to 1. So the equation 6 shows that conditional distribution function is never smaller than the ordinary distribution function. A similar statement can be made for conditional density function also. We can go through the problem here. This type of problem is very important. Frequently they will be asking you. Here also some problems are there. Please, I'll be sharing this document to your email address. Please go through it. All these problems are very important. All these problems are asked in previous percentages also. Thank you. This is about the first unit.